Greetings and welcome to the Chemistry 223 Exam 2 Review, where we're going to go over some questions which are very similar to ones you might see on the second midterm coming up. The second midterm will cover chapters 15, 16, and 17. Chapter 15 was on the solubility of compounds. Chapter 16 was thermodynamics, especially with entropy and Gibbs free energy. And chapter 17 is on electrochemistry. So knowing all of that, let's go over some questions and stuff that you might see on the second midterm exam. If this is an online class of Chem 223 that you're taking, then the midterm exam will have 20 multiple choice questions. There'll be somewhere between 3 and 4 short answer questions. Kind of depends what I feel like when I make the exam, but something like that. There will be a deadline for turning in the midterm exam. It'll be on Friday at 9 a.m. via email. And when you get the exam back, I will return it with a summary sheet. And the summary sheet, which will be at the very end of the midterm I return to you, will list, first of all, how you're doing in the class. I do encourage you to check that out. Make sure that the grades that I have for you are the grades that you actually got. Once in a while, I do make errors. It's true. Also, if you're missing a lab, it'll tell it there. And you want to make sure you get all your labs into me to get that lab completion bonus, stuff like that. If this is not an online class, i.e. if this is face-to-face, then we'll have some different set of instructions. And regardless of if you're taking Chem 223 as an online class or face-to-face, if you do have questions on anything, and that includes like what's due or when it's happening and stuff like that, please contact me. Email is awesome. I will get back to you really soon. I want to make sure that you know what to expect when the midterm happens. No surprises. That's kind of the name of the game. Okay, so without further ado then, let's get into some questions where I'll show a question. There'll be a time that you can pause the video, work on the question a little bit, and then when you're ready, you can unpause the video. We'll talk about the answer. Let's get into the review. The first question, it says, decide if a precipitate will form when mixing the indicated reagents, and we'll assume that all the concentrations are 1 mole per liter. And the answers are yes, no, or who knows. Well, I'll be honest, who knows is not one of the answers, not the correct answer anyway. See if you can figure this out. If you want, you can pause the video, work on it, and when you're ready, unpause the video. We'll talk about the answer. Pause the video now. At this point, I'm assuming you've worked on the problem and you want to talk about the answer, so let's do it. This question is really a flashback to Chemistry 221, when we talked about if solids are formed or if things are soluble, stuff like that. And this is a question that you can use and answer based on the solubility table, all right? Chlorides, like bromides and iodides, are usually water soluble. They're usually AQ when you write them with compounds. For example, with K right here. However, if you're going to combine chloride with lead, all right, lead to chloride is one of the exceptions. We talked about in lecture how lead 2 plus, silver plus, and that weird mercury 2 plus, those are all ions that form insoluble compounds with chloride, bromide, and iodide. So in this reaction, you can think about the K and the lead as trading places with each other. On the other side, you would have KNO3, and the lead, which was 2 plus on the right, would be 2 plus on the product side as well. It needs 2 chlorides. You would make PbCl2. And if you balance this out, you would put 2's right there. Anything with potassium or nitrate is aqueous, and so that includes KCl and PbNO3. It also includes KNO3 on the product side. On the other hand, PbCl2, chloride is an exception when it's with lead. This one will be insoluble. So you would expect a precipitate, a solid, to form, all right? This is a little bit of a review from Chem 221 material. This is a double displacement or exchange reaction, and in this type of double displacement, you're forming a solid. So the net ionic reaction would be lead 2 plus 2 chlorides making PbCl2. Most of the time, chlorides, bromides, and iodides are water soluble, AQ, unless they're with silver plus, lead 2 plus, as is in here, and mercury. The solubility of barium fluoride is apparently 3.6 times 10 to the minus 3. So what would be a reasonable value for Ksp for barium fluoride? So think about what it means to go from a solubility to a Ksp B for barium fluoride. I recommend you pause the video, work on it a little bit. When you're ready to talk about the answer, unpause the video, and that's what we'll do. Pause the video now. Okay, I'm assuming that you've had a chance to work on this problem and you want to talk about the answer, so let's do it. KSPs, like all KSPs, the solid is the reactant, so BAF2 solid, and it's an equilibrium, it's a type of K, and the products are always the ions that go into it. So that would be the barium ion and 2 fluorides, okay? So as barium fluoride dissolves, to a little bit anyway, it's going to make barium ions and 2 fluoride ions. Now, solubility is literally a moles per liter, and it's a number that tells you how many moles of barium fluoride, in this case, are dissolving per liter, all right? Well, Ksp is different than solubility. Ksp would be the barium concentration times the fluoride concentration squared, okay? So we need to think about how solubility relates to Ksp. And like we kind of saw in lecture, if you say that the barium fluoride is X, and that represent how many moles per liter of barium fluoride break up, then X moles of barium fluoride that break up will make X moles of barium because they're 1-to-1 stoichiometry, and 2X fluoride because you get twice as many fluorides out as you do bariums. It's a 2-to-1 ratio. So X here is that 3.6 times 10 to the minus 3. So if you want to get really fancy, well, over here, barium we said was X, fluoride was 2X, but we square it. This is a 4x cubed equaling Ksp problem like we saw in lecture. If you have 2 anions and 1 cation, or 2 cations and 1 anion, the relationship between solubility X and Ksp is going to be this Ksp equals 4x to the third power. So the easiest way to do this problem then would be to have 3.6 times 10 to the minus 3, which is X, raise it to the third power, multiply it by 4. Now, you could also take 3.6 times 10 to the minus 3 and then multiply that by 2 times 3.6 times 10 to the minus 3 and square that. That would be like finding barium and fluoride separately, and that's okay too. Any way you want to do it, the answer should come out to be 1.9 times 10 to the minus 7th. And you can see down here, that's what I did. I had 4 times the solubility to the third power, and again, that came from X for barium, 2X for fluoride squared. That's where the 4x third comes from. Oh joy. Ksp is different than solubility, all right? Barium fluoride, if you place it in water, 3.6 times 10 to the minus 3 moles of barium fluoride will dissolve per liter. So if you get, say, 3.61 times 10 to the minus 3 moles of barium fluoride, you're going to see a solid compound form. But if you're under that threshold, under that 3.6 times 10 to the minus 3, no solids will be observed. Ksp is the product of solubilities, Ksp, all right? So you can deconstruct a Ksp into solubility, or as we did here, you can take the solubility and determine the Ksp, but they are different quantities, different kinds of numbers that you can use in different situations. This question says, which lead salt, those are all lead salts, has the greatest molar solubility in water at 25 degrees Celsius? And there's 3 different numbers right there. So these are KSPs, and we're asking about which one has the biggest molar solubility, okay? So see if you can answer this question. I recommend pausing the video. When you're ready to talk about the answer, unpause it. Pause the video now. At this point, I'm assuming you've tried the problem and you're ready to talk about the answer, so let's do it. All of these lead salts, which are lead ionic compounds, by the way, all of these are 1-to-1 cation anion. So 1 lead to 1 carbonate there, 1 lead to 1 sulfide there, and 1 lead to 1 sulfate, all right? So they're all 1 cation, a lead, to 1 anion, whatever it is. And why that's important is that the solubility solubility, which is really what we're looking for, Ksp is going to equal solubility squared, all right? So if you want to truly translate the Ksps into solubility, X would equal the square root of Ksp. So you can literally go through those Ksp values, take the square root of them, and a number that pops up, that is the solubility, and the biggest solubility would be the answer here. That's totally fine if you want to do it. Another way to think about it, K, as it gets smaller and smaller, or closer to zero, but never getting to zero, as K gets smaller, you have more reactant-favored conditions, all right? And more reactant for Ksp means more solid. So the biggest Ksp will have the most solid dissolved. It should have the greatest solubility. And you can see the first two Ksps are very small. The third one is small, 10 to the minus 4, but compared to the other ones, that's large. So my money would be on answer C here, because the biggest solubility should come from the biggest Ksp, most product favored. And sure enough, that's exactly what it is. PbSO4 has the biggest solubility. Largest Ksp means most product favored. Most product favored means most ions in solution, and that's what solubility is all about. If you have more ions in solution, you'll have the greater solubility. We would expect PbSO4 to precipitate last if you're adding equal amounts of the other ones, etc., etc. We have a solution containing 0.10 molar potassium sulfite and 0.30 molar sodium sulfate. And we're adding slowly calcium nitrate, which precipitates first calcium sulfite or calcium sulfate. And there's Ksp values. Now, both of those Ksps are less than 1, so that means that a solid will form pretty readily, but one of them will form first. See if you can predict which one it is. Answer 42 is not correct. That's my stupid attempt at humor. If you ever get a chance to read or watch The Hitchhiker's Guide to the Galaxy, they asked this supercomputer about the meaning of life, and it said 42. It's kind of funny if you're in that context, but here it sounds kind of dumb, so my apologies. The answer will be A or B. See if you can figure out which one it is. If you want to pause the video, that's cool. Work on it. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you had a chance to work on this problem and you want to talk about the answer, so let's get into it. Ksp, all right, is going to equal, in both of these cases, Ksp is going to equal the calcium ion concentration times the sulfite, if it's CaSO3, or in calcium sulfate, Ksp would equal calcium times the sulfate. So one thing you could do in this problem is take those Ksps and divide by the sulfite concentration or the sulfate concentration. And whatever then the smaller number is, that's going to be the solid that precipitates first. All right, that would be a great mathematical way to do it. But if you just look at the Ksps, I mean, 10 to the minus 8th is several orders of magnitude smaller than 10 to the minus 5. Remember, 10 to the minus 5 is bigger than 10 to the minus 8 in this kind of world. So 10 to the minus 8 divided by the sulfite concentration, 0.10, that's going to be, I think, 1.3 times 10 to the minus 7. And that's already pretty small compared to 2.4 times 10 to the minus 5. So in this problem, because the Ksp for calcium sulfite is so much smaller, I would argue that the calcium sulfite will precipitate first. And if you don't believe me, and I totally understand, here's the math for the calcium sulfite and the calcium sulfate calculations. You take the corresponding Ksp and you divide by either sulfite or sulfate, and you can see that 1.3 times 10 to the minus 7 moles per liter, that's the calcium required to make calcium sulfite precipitate. For the calcium sulfate, you need 8 times 10 to the minus 5 moles per liter calcium. That's quite a bit more than 1.3 times 10 to the minus 7th molar calcium. So the calcium sulfite precipitates first. The calcium sulfate will precipitate last. It takes extra calcium to make that one precipitate out, and that's what you can do. But again, most of the time, smaller Ksp will be the one to precipitate first. If you want to nail it down, you'll do this kind of process. And in these problems, the calcium to sulfite or sulfate ratio was 1:1, so Ksp is totally fine to use. If you had like 2 metals to 1 anion and a 1:1, then you may want to do this process where you actually calculate the calcium concentration. Calcium sulfite precipitates first, we saw in the last problem, as calcium ions are adding to the solution of 0.1 molar potassium sulfite and 0.3 molar sodium sulfate. The question here, this is an interesting extension, is what is the sulfite concentration as the calcium sulfate begins to precipitate? So it's good to visualize here in your mind what's happening. Calcium sulfite is precipitating first, and as the calcium sulfite precipitates, the sulfite concentration, which was 0.10 moles per liter, that's going to decrease, okay? So this question is saying, what is the sulfite concentration when the other compound with sulfate begins to precipitate? The answer will be a number less than 0.1, okay? And you can actually calculate it. You'll need the calcium ion concentration required to make calcium sulfate precipitate out. So anyway, see if you can make sense of all of this. It's going to be one of the answers listed right there, and no, it's not 42. Darn it. Anyway, I recommend pausing the video. You can work on it, think about it a little bit, and when you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've tried the problem. You're ready to talk about the answer, so let's do it. Okay, so we saw in the last problem that calcium sulfite precipitates first. Smaller Ksp, smaller amount of calcium required to make precipitation happens. In this part of the question, we want to know how much sulfite is left as the calcium sulfate, the more soluble thing, begins to precipitate. All right, so what we're going to do here is we're going to remember that calcium sulfite, the Ksp, it equals the calcium times the sulfite. And what we want to know here is we want to know how much calcium is needed to make calcium sulfate precipitate. And in the answer for the last problem, I actually calculated that. But whatever that number is, that's what we're going to put in right there, okay? We'll solve for this number, the new sulfite. It'll be a number less than 0.10, and until you do the math, sometimes it's hard to see what that answer is going to be. So in this problem, the answer comes out to be 1.6 times 10 to the minus 4. But let's go through here and figure out what's exactly going on. First of all, like I said, you need to figure out the calcium required to make the calcium sulfate, the more soluble thing, make a solid. So you take the calcium sulfate Ksp, 2.4 times 10 to the minus 5, you divide it by the sulfate concentration, 0.30, and you need to make the calcium ion 8.0 times 10 to the minus 5 moles per liter to make the calcium sulfate precipitate. Well, this is the amount of calcium needed to make that other salt form a solid, all right? So we're going to use this number down here in the new version. When I use the arrow, that's this number right there, all right? So you can see down here at the bottom, we're using the Ksp for the calcium sulfite. We're using the calcium from the sulfate. Ksp for that one divided by calcium for that one, 1.6 times 10 to the minus 4. So chemists would often consider this to be a separation. It started at 0.10 sulfite, molar sulfite, and it went down to 1.6 times 10 to the minus 4 molar sulfite. So that's, roughly 3 orders of magnitude smaller. That's pretty good. On the other hand, the sulfite is certainly not 0, and that's maybe what you'd want it to be if you're going to truly separate out things. But this at least gets a lot of the sulfite away from the sulfate, which is kind of a cool thing. Here's a question. What is the pH of a saturated solution of magnesium hydroxide? And it gives the Ksp there for magnesium hydroxide. See if you can figure it out. This is a review of the pH problem. And you can think about magnesium hydroxide, by the way, as a strong base. Anyway, see if you can figure out which one of those answers it's going to be. I recommend you pause the video, work on the question, and when you're ready to hear the answer, you can unpause the video. We'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on the question. You want to think about the answer. Hey, let's do it. Knowing Ksp and the form of the Ksp expression can be really helpful for a problem like this. So Ksp, which is defined by the magnesium hydroxide solid as the reactant, going to magnesium ions and hydroxides as products, you would write here that Ksp equals magnesium ion times hydroxide ion squared, okay? So if we could find the solubility of magnesium hydroxide from the Ksp, solubility could be defined as X magnesium and 2X hydroxide. So what I would do on a problem like this is I would break the Ksp down to a solubility X. This is a 1 cation to anion ratio. This is 4x cubed equals Ksp. So to solve for x, Ksp divided by 4, and you take the cubed root of it, that'll give you the the solubility of the magnesium hydroxide. Now, magnesium hydroxide solubility, to figure out hydroxide, which is getting closer to what we want, we have to multiply the solubility by 2. That's one little trick in there. So once you get solubility, multiply it by 2, and that will equal hydroxide. And from there, you can find hydronium from Kw, and then pH equals minus log hydronium, or you can find POH equals minus log of OH, and then 14 minus POH equals pH, and either way is fine. Right away, though, you can automatically disqualify answers A and D. Those are both pHs. If they were pHs, that would be acidic, and that doesn't really make any sense. Hydroxide is a base former. It should have a basic pH. So anyway, here's all of the math. First thing to do, think about what solubility is all about. And because this is a Ksp, magnesium hydroxide is in equilibrium with magnesium 2+ ions and 2 hydroxides. So 2 anions and 1 cation means this is a 4x cubed equals Ksp problem, where x is the solubility. So to solve for x, you take the Ksp, divide by 4, raise it to the 1/3 power. That would be like caret parentheses 1/3 parentheses in your calculator. Try it out if you haven't done this before. This is a good skill to have. But the solubility comes out to be 1.1 times 10 to the minus 4 moles per liter. And again, that number means that 1.1 times 10 to the minus 4 moles of magnesium hydroxide dissolved per liter. But we're after the dissolved hydroxide, because hydroxide is what's going to lead us to pH. There are 2 hydroxides for every 1 magnesium hydroxide that does dissolve. So 2 times x, 2.2 times 10 to the minus 4, that's the hydroxide ion concentration. And then what I did in this problem is I first solved for hydronium. Hydronium equals Kw divided by hydroxide, 4.5 times 10 to the minus 11th. And once you have hydronium, minus log of hydronium, 10.35. Now you could have also solved for POH once you had hydroxide, and then 14 minus POH should also give you the pH of 10.35. Either way is cool. KSPs can be helpful in finding pHs. I know you think you're like, oh, I'm so sick of pH after the first midterm, but trust me, it is something that's big time in chemistry. All right, what can I say? This is just another tool that is sometimes helpful when you have a KSP and you need a pH value. This is the kind of question you might run into. We've got a solution. It's got a lead 2 plus concentration 0.0012 and a chloride ion concentration 0.01. Will you see a precipitate? All right. And there's the KSP for PbCl2. So on questions like this, it's basically yes, no. I could have put my 42 in there, but that's just too silly at this point. I didn't do it. See if you can figure out if this is going to form. All right. Pause the video, work on it. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem. You want to see what the answer is, so let's check it out. There are different ways to solve this problem, all right? But what I would probably do is I would do what they call a Q versus K comparison. And Q for solubility looks the same as a KSP. So Q for us here would be the lead concentration that's given times the chloride ion concentration that's given squared. And that number Q you can compare to K. If Q is less than the Ksp, no precipitate would form. But if Q is greater than the Ksp, then that would mean a precipitate would form. And that's a totally cool way to do that. Another way you could do this problem is you could, for example, take the Ksp that's given and divide it by, we'll say, the lead concentration. That'll tell you the chloride ion concentration squared that you need, and you could compare it that way, which would be fine. Again, I'm more of a K and Q kind of person, classic chemist, but you can do it multiple ways. Either way, you should see that the PbCl2 does not precipitate. So what I did down here is this is what I did. I solved for the Q. Q looks just like K. It's lead times chloride ion squared. So I put those numbers in. 1.2 times 10 to the minus 7th was my Q. That Q is less than Ksp, so that means no solid form. Again, if you did this same calculation and you got a Q that was greater than Ksp, then that would mean that your solid does form. That's just the way I roll, but there are more than one way to do this problem, and you should do the way that works best for you. Which of the following shows the correct formation constant Kf equation for CrCN6-3? This is a complex ion, and complex ions are defined by their formation constant Kf expressions. So see if you can figure out which one of those would be the best answer for this problem. Pause the video if you'd like to. We'll work on it when you unpause it later. Pause the video now. Okay, I'm assuming you've had a chance to work on the problem and you want to talk about the answer, so let's get into it. Ksps, which is what most of this chapter is about. Ksps, you have the solid as the reactant, and the ions that go into it are the products, all right? And that's for Ksp. But complex ions have kind of the opposite form of an equilibrium expression. In a complex ion, you want to have the complex ion be your only product, and whatever needs to go into it, those are going to be the reactants. So if you look through all of these examples, all right, the very last one, this is the complex ion, CrCN6-3, and everything that's needed to go into it would be a chromium 3+ and 6 cyanides. So with all of those answers right there, it's going to be E. The complex ion is supposed to be the only product, and whatever's needed to go into it as ionic forms is going to be a reactant. There was no mention of like solids, so a lot of these are just honestly kind of silly. Answer D would be more like a Ksp expression. It's the opposite of what we need here. In a Ksp, the solid would be the reactant and the ions that go into it are the products. But for formation constants, Kfs, you want to have the complex ion be the only product, and whatever is needed to go into it will be the reactants. This question states, calculate the standard entropy change for the following reaction. This is a reaction where carbon tetrachloride reacts with oxygen to make CO2 and chlorine gas. And there are 4 entropy values listed right there. See if you can remember what we talked about in lecture to calculate the entropy change for this reaction. I recommend you pause the video, work on it, and when you're ready, you can unpause it. We'll talk about it. Pause the video now. Okay, at this point, I'm assuming you've had a chance to work on the problem and you want to talk about the answer. Let's do it. These kind of problems, all right, it's usually all of the products minus all of the reactants. This is an entropy problem, so you'd say it would be the entropy of the products minus the entropy of the reactants. And you can see all the values are given for you right there. So for this problem, what that means is you would take the CO2, which is the one product, and 2, by the way, times the chlorine, 2 because of the stoichiometry of 2 for the Cl. You would take those two together, those are the entropy of products, and you would subtract the entropy of the reactants, which in this problem is CCl4 and O2. So the 2 times the chlorine plus the CO2 minus the O2 minus the CCl4, and this is just something for your calculator. And when you do that, you get an entropy change 240.44 joules kilojoules per Kelvin. This is an increase in the entropy. But just try and focus on the form. This is the official version of the equation. It's the entropy of the reaction equals the sum of, that's what that symbol means, the sum of all the entropies of products minus the sum of all the reactants entropy. And you just plug and chug the different numbers in. Make sure you multiply the chlorine by 2 because stoichiometries are affected. These entropy values are usually per 1 mole. Shouldn't be too bad. In this question, I want you to calculate the Gibbs free energy for this reaction, which is methane and oxygen making CO2 and water, okay? And there's some values for the Gibbs free energy and 5 possible answers. See if you can figure out which one of those answers makes the most sense. I recommend pausing the video. You can work on the question, and when you're ready, unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to try the problem and you want to talk about it, so let's do it. Okay, this kind of problem is similar to the last one we did with entropy, but this one now is about Gibbs free energy, delta G. But it's the same kind of process, Gibbs free energy of the products minus Gibbs free energy of the reactants. So for this problem, you would take the Gibbs free energy of the CO2 and 2 times the water, don't forget the stoichiometries, and you would subtract the Gibbs free energy of the reactants, the Gibbs free energy of the methane, plus 2 times the Gibbs free energy of the oxygen. But wait, there's no oxygen listed for Gibbs free energy. Wah! And about this time, you probably want to run around and go, that's it. I'm, going to go be a janitor or something. But don't you dare. We're almost to the end of Chem 223, so you hang on with me. But anyway, I digress. Notice here that oxygen was not included. Okay, and that's intentional. Oxygen is an element in its standard state. It's a gas. It's not a liquid or ozone or something like that. Elements in their standard states have delta G's equal to 0. This is the same for enthalpy delta H. If you have an element in its standard state, the delta G and the delta H value will be 0. For entropy, you'll always have positive numbers because the only time you have a 0 entropy is that perfect crystal at 0 Kelvin, which is never. So positive entropies are definitely going to happen for everything in a reaction. But when it comes to delta G products minus reactants or delta H products minus reactants, the elements will have a 0 value. So after this, it's just a thing to do in your calculator. Here's the same kind of thing. Delta G of the reaction equals the sum of the delta G's that are products minus the delta G's that are reactants. And again, you can see down here that oxygen is 0, so that's why it was not there. It's a good learning moment. Oh, those darn educators. Anyway, delta G, negative 800.8. Negative delta G's means spontaneous. This reaction will occur. This is the burning of methane, which is essentially natural gas. So all the times we've used Bunsen burners in the lab, or you've watched me use Bunsen burners if this is a virtual course, all the times that we have or might use Bunsen burners, you're going to have something happen. So delta G had better be a negative number. We should be able to burn methane, and we can. Oh, chemistry. Here's a reaction where magnesium is reacting with oxygen to make magnesium oxide. And given the information below, I'd like you to calculate delta G for this reaction. And delta H and delta S are listed. Okay, so use that information, see if you can figure out what the answer is. I recommend pausing the video. When you want to talk about the answer, unpause it and we'll talk about it. Pause the video now. Okay, at this point, I'm assuming that you've had a chance to work on the problem and you want to talk about the answer, so let's do it. This is a problem where you want to use what's called the Gibbs free energy equation. And the Gibbs free energy equation is delta G equals delta H minus T delta S, okay? And delta H is literally that delta H value that's listed right there. Delta S is the value of delta S listed there, and T is the temperature. Now, delta H is in kilojoules, and notice that delta S right now is in joules. You want to make sure that you're using joules and joules or kilojoules and kilojoules. And since all of the reasonable answers are given in kilojoules, I would convert delta S to kilojoules. You can do that easily by dividing by 1,000. You could use minus 0.10836 if you'd like, and that would be a kilojoules per mole value. The other thing though, just to make sure everybody's everybody's clear, you want to make sure for temperatures you use Kelvin. So 25 Celsius plus 273 would give you a Kelvin temperature of 298 Kelvin. So after this, just plug and chug in the different numbers. Again, you can see there's delta S divided by 1,000. I used Kelvin temperatures, negative 568.9 kilojoules per mole of reaction, which means that's how much Gibbs free energy there is. This is a negative delta G, so that means spontaneous. This reaction will occur. And if you've ever seen magnesium burning in oxygen, it's incredibly bright, very, very bright reaction. This is an enthalpy-driven reaction. Enthalpy, when it has a negative number, is contributing towards the negative delta G. So negative delta H means enthalpy-driven. If this reaction were to be entropy-driven, you'd have to have a positive delta S, but this delta S is negative. And that kind of makes sense because you're going from 1.5 moles of reactant to 1 mole of product. You're getting rid of a gas, which is always entropy favored. Entropy doesn't like this reaction. This is not an entropy-favored reaction. If it was a positive delta S, then you would have an entropy-favored reaction as well. So this one is enthalpy-driven, but not entropy-driven. We have a reaction which has a positive delta H and a positive delta S. And what can we say about the reaction spontaneity at different temperatures? Okay, before we get into the answers, we're going to go back. Delta G equals delta H minus T delta S. That's going to be the equation we want to use here. And if it's talking about reaction spontaneity, spontaneity means delta G. If it's spontaneous, delta G will be negative, okay? So you have 4 possible answers there. See if you can use this information to see which one is the best fit. I recommend pausing the video. You can think about it. When you're ready to hear what the answer is, unpause it. We'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on the problem. You want to hear the answer? Let's get into it. Positive delta H means endothermic, and a positive delta H makes delta G want to be positive, all right? Positive delta H makes positive delta G. This is not an enthalpy-driven reaction. If it's enthalpy-driven, you'd have a negative delta H. On the other hand, delta S, if it's positive, a positive times negative T, that's going to make that whole part right there negative. So a positive entropy does contribute to a spontaneous delta G, i.e. a negative delta G. This reaction is entropy favored. So this is an example where enthalpy and entropy are kind of fighting. Enthalpy does not want this reaction to occur. It's a positive delta H. On the other hand, entropy does want this reaction to occur. Positive delta S times negative T makes delta G want to be negative. So the two species are fighting, and when you have them fight, when they're both the same sign, then what's going to be the deciding part is literally the temperature. As temperature is higher, all right, it'll help the delta S term to win. On the other hand, if the temperature is lower, then that will make T delta S small, delta H will dominate. Small t helps make delta H win, if you will. So in this problem, delta S wants the reaction to go. High temperatures will make this reaction product favored, all right? Low temperatures will favor the delta H term, which will make the reaction less likely to occur. So positive delta H does not make reaction spontaneous, but positive delta S does support spontaneity. So when you have a higher temperature, negative T delta S will overpower delta H, making the reaction overall spontaneous, i.e. giving it a negative delta G. High and low temperature are very vague, all right? You can actually calculate what the temperatures are, and that threshold temperature, any temperature above would be considered high, and any temperature below would be low. But it does vary on the magnitude of delta H and delta S. Knowing at this point, without knowing the actual values, we can't see anything more. So high and low is just relative, all right? But it does kind of give you a sense. If you wanted this reaction to go, you'd want to pump up the temperature to try and make it overpower the delta H and make the reaction spontaneous. In this problem, we have a series of delta H and delta S values, and we want to calculate the delta G for this reaction, which is 2 hydrogen peroxides decomposing into 2 waters and an oxygen. And there's 4 reasonable answers and 1 silly answer there once again. Okay, in a problem like this, you want to find delta H, products minus reactants. You also want to find delta S, products minus reactants. Then you're going to combine your delta H and delta S into the Gibbs energy equation, delta H minus T delta S equals delta G, and that'll give you the answer. So try and work on this question by yourself. I recommend pausing the video. When you're ready to hear the answer, you can unpause it. We'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to dig into it, so let's do it. Like I said, this is kind of like a 3-step process. First, you're going to find the delta H of the reaction. So that'll be delta H of the products, water and oxygen, and you'll subtract the delta H of the reactants, hydrogen peroxide, and you'll end up with some delta H of the reaction value. Then the second step is to do the same thing but for entropy. So you'll take the entropy of the products, water and oxygen, and subtract the entropy of the hydrogen peroxide, and that'll give you the delta S of the reaction. And then finally, delta G equals delta H minus T delta S. All right, make sure you turn the Celsius into Kelvin. Make sure you turn the joules into kilojoules for entropy. I'm doing it because all the answers are in kilojoules, so it'll make it easier to understand. Not too bad. A little bit of math, but not too bad. So when you do that, I got out answer D. And let's break this down here, how we did it. So first step, find the delta H of the reaction, which is delta H products minus delta H reactants. There's no O2 delta H value listed. That's because elements in their standard states have delta H's equal to 0. This is similar to what we saw with the delta G values. Remember, delta G and delta H will be 0 for elements in their standard states. So delta H minus 196.0 kilojoules per mole. Now delta S, all the values will be positive, so you'll have to look up everything, including the elements in their standard states. So delta S, products minus reactants, and make sure you include the stoichiometries of 2 in both delta H and delta S reactions. Delta S comes out to be positive, 125.7 joules per mole Kelvin. Finally, you plug all of this into delta G. Delta G equals delta H minus T delta S. I do recommend that you turn the joules into kilojoules right there. So I divided by 1,000, 0.1257 would be the kilojoules. That way I have kilojoules and another kilojoules number. You don't want to use joules and kilojoules. That would mess everything up. Anyway, if you did it all right, minus 233.5 kilojoules per mole of reaction, answer D. You got this. This reaction is spontaneous, negative delta G. It is enthalpy favored because delta H is negative, and it's also entropy favored. Delta S is positive. So this reaction is going to go all the time, all temperatures. Delta H and delta S want this reaction to go. In this reaction, we have delta H negative 96.0 kilojoules per mole and delta S negative 12.6 joules per mole Kelvin. If the temperature is increased slowly, at what temperature will this reaction become non-spontaneous? And there's 5 possible answers there. One of them doesn't make any sense. But anyway, I want you to think about this question. This is when you're trying to find that threshold temperature when delta H and delta S are fighting. And notice here that delta H and delta S are both negative. If delta H and delta S have the same sign, that means they're going to fight. All right, that's kind of a weird way to think about it, but it's true. Anyway, see if you can figure this out. Pause the video. You can work on it. When you're ready to hear the answer, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on this question and you want to hear what the answer is, so let's do it. The Gibbs free energy equation, delta G equals delta H minus T delta S. When delta H is negative, it means it's enthalpy driven. This is an enthalpy driven reaction. But when delta S is negative, all right, delta S is not happy in this reaction. If delta S is positive, it's going to be entropy driven. This is not entropy driven. So they're fighting here. And delta S does not want this reaction to occur. Delta H does. So as temperature goes up, eventually delta S is going to be able to overpower delta H, and the reaction will become non-spontaneous, i.e. when temperature is large enough, the T delta S term compared with delta H will make delta G a positive number. It will no longer be spontaneous. So in this question, what you want to do is you want to let delta G equals 0, because 0 is the threshold between being spontaneous and non-spontaneous. So delta H will equal T delta S, or T is going to equal delta H divided by delta S. And the temperature that pops out will first of all be in Kelvin. And second of all, that's going to be the threshold between spontaneity and non-spontaneity. Lower temperatures in this problem will be spontaneous. They'll give you negatives, but higher temperatures are the ones that are going to give you the non-spontaneous. Now, again, delta H is usually in kilojoules. Delta S is usually in joules. So I would recommend converting the delta S to kilojoules, or if you want delta H to joules, doesn't really matter. Want to make sure you use the same kind of unit. But when you do that, and down here you can see that I turned delta S into a joules, or into kilojoules, excuse me. The temperature that pops out, 7,620. That's a Kelvin temperature, all right? And 7,620 Kelvin is the threshold between when a reaction goes from being spontaneous to non-spontaneous. Now remember that lower temperatures were spontaneous, so you can imagine that up to 7619 Kelvin, this reaction would be spontaneous. It would occur. But once you get just a little bit above this temperature, like 7621 Kelvin, then the reaction will be non-spontaneous, and it won't happen, because above 7620, that's when delta S is able to overpower delta H when you multiply delta S by negative T. So this is kind of how these things work. You'd want to keep this temperature somewhat lower if you could, trying to stay away from this non-spontaneous threshold, but this is how you can calculate things like that using the values of delta H and delta S. Here's a question. Barium sulfite is poorly soluble in water. It has a Ksp 8.0 times 10 to the minus 7th, again, much less than 1. What is delta G at 25 degrees Celsius? Again, 5 answers, 4 of them being potential answers. See if you can figure out what the answer is. Pause the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you had a chance to work on it. Let's figure out what the answer is. This question is converting a K into delta G. And what we talked about in lecture is that delta G equals minus RT natural log of K. And again, this is really sloppy. I'm really sorry. But delta G on the left side here equals negative RT natural log of K. K can be any kind of equilibrium constant, Ksp, Ka, Kf, whatever. Okay, so you'd literally for the K, you'd put in 8.0 times 10 to the minus 7th. T is the Kelvin temperature, so 298 Kelvin, and R is the energy R, the 8.3145 number. One thing that will help is that K's less than 1 are reactant favored, and a delta G for a reactant favored condition will be a positive number. A negative delta G would be like a product favored, and that would be like a K greater than 1. So there's no way that the answer is going to be C. C, a negative delta G, would only come from a K larger than 1. So this is just one of those problems you got to plug the math in. You'll probably get joules per mole Kelvin out first, so you can divide by 1,000 to get kilojoules. Anyway, if you do that, you get 34,800 joules. Divide that by 1,000, 34.8 kilojoules per mole reaction. So again, K's less than 1 correspond to delta G's, which are positive, and that's kind of an important thing to remember. Just like if you had a K greater than 1, you would end up with a delta G, which was negative. Here's a reaction where I want you to balance this reaction where permanganate reacts with iodide to make manganese 4 oxide plus iodine. But also pay attention to the pH. This pH is 8.37. So see if you can figure out which one of those represents the balanced chemical reaction for this reaction at a pH of 8.37. So I recommend that you pause the video, work on it, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've had a chance to work on the question and you want to hear about the answer, so let's get into it. This is a problem where you're balancing a redox reaction, and the pH becomes really, really important. Remember that pH is greater than 7 are basic, and basic pH balancing equations at the end won't have any H plus in them. They will only have hydroxides and water. If you had an acidic pH, you would end up with H plus ions and water. But for this one, in base, you want to make sure that it's just hydroxides and water. What I recommend on a problem like this is first you break them down into the 2 half reactions. And that just means put the similar species together. So for example, I would put the 2 manganese species together for 1 half reaction, and I would put iodide going to iodine for the other one. They look kind of the same. And then what you want to do is you want to balance for mass, so you'd have to add 2 iodides to make the iodine. When it comes to the permanganate, that's when you have to think about water and hydroxide. And again, for bases, you can do it first in acid and then do it in base later, neutralize it, or you can do it directly in hydroxide and water. Either way is fine. You want to make sure you add electrons to make sure the charge is balanced. And before you add the 2 half reactions, you need to make sure that the electrons cancel out. You don't want to show electrons in any of the final equations. So at this point, let's just look at the work and see how this is done. So what I did in my answer here is I balanced first in acid. And like I said in lecture, I'm a lot better about balancing things in acid than I am in base. For some reason, hydroxide and water gets very confusing to me. So what I do is I balance in acid first, and then I go back and balance in base. This way does take longer than if you use hydroxide and water, but it works all the time for me, and if it works all the time for you, you should do it this way too. So anyway, I put the manganese parts together. If this is an acid, then because there's 4 oxygens and only 2 oxygens, you need 2 waters, but in acid, that would mean adding 4 H plus to balance it. And then making sure the charges are okay on both sides, you need to have 3 electrons as reactants. And for the other one, like we said, we needed 2 iodides. That means you'll need 2 electrons on this side. At this level, you should have one piece which has electrons as reactants. That's the reduced side. And you should also have 1 half reaction where electrons are products. That's the oxidized side. The next step is to combine the 2 half reactions, but you want the electrons to cancel out. So in the first reaction, we have 3 electrons, and in the second reaction, we have 2 electrons. So what we do is you can multiply the first reaction by 2, and that's what's given right there. So you can see everything is multiplied by 2. And the second reaction, we multiply everything through by 3. So that's why we end up with 6 electrons and 6 iodides, etc., etc. That way, when you combine the 2 reactions together, the electrons are absolutely out of here. You don't want them around. And this is the balanced reaction if it were an acid, if your pH was less than 7. But our pH is not greater than 7. So in this way, which is longer, now what we have to do is you have to add just as many hydroxides as you need to get rid of all the H+. So what I would do here is I would add 8 hydroxides to both sides in order to get rid of the 8 H+. Now H++ plus OH- makes water. So that would make 8 waters on the reaction reactant side, and on the product side, I would still have my 8 hydroxides. If you add something to one side, you have to add it to the other side. Works in math and it works in chemistry too. At the end, you have to make sure that the waters on both sides cancel out, because chemists love to keep things as simple as possible. So as you can see, there's some steps here, but let's talk about them. So first of all, here's the 8 hydroxides being added to both sides. The 8H plus and 8OH minus make 8 waters, and I still have my 8 hydroxides there, but I need to now take care of the excess waters. So I'll subtract 4 waters from both sides, and bam, answer D is the answer. And this one now is balanced in base for a pH greater than 7. It has hydroxide and water, but there's no H plus. So again, this is the way that works really well for me. And if you can do this without going through acid first, honestly, that's great. And a lot of people can, all right? But for whatever reason, I've got a mind block going or something. So this acid first and neutralize in base later is the way that I use myself. You do the way that works best for you. We have a bunch of reduction potentials. Reduction means electron is a reactant, and most of the tables of electrocell potentials are listed as reductions. But anyway, here's a whole bunch of them. And what I'd like you to do is tell me which one of those is the strongest reducing agent in the list. Okay? Figure out which one of those is the strongest reducing agent in the list. So think about this a little bit. I recommend pausing the video. You can unpause it when you want to talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answers, so let's do it. The hardest part I find for people on this problem is to realize that these are reductions, but we want the reducing agent. Remember, reducing agent is not reduction. The agents is like the opposite, okay? So reducing agent means oxidized. You want the strongest oxidizing species in the list. So really, in this problem, what we have to do is, if you're talking about oxidation, you have to flip all of these reactions around. And if you flip a half cell reaction around, it's no problem. For the first one, you'd end up with cerium 3 plus as the only reactant, and the products would be cerium 4 plus an electron. When you flip a reaction, the E cell value is changed as well. So positive 1.61 becomes negative 1.61. Delta G is the way to tell which one is the strongest, and delta G equals minus NFE. So what that tells a scientist is that positive E values will give negative delta G's. And if you want the strongest one, that means you want the most spontaneous, the most negative. That would mean the most positive E cell potential is what you're after. So remembering here that we're flipping everything around, all right? If you flip the last one, all right? If you flip the aluminum one, so you end up with aluminum metal making aluminum 3 plus 3 electrons, well, that's being oxidized. Aluminum would be the reducing agent. That would have a value of positive 1.66 volts. And that's the biggest voltage of all of these. Aluminum is going to be your best reducing agent. It is most likely to be oxidized. That's what reducing agent means. And I know that's confusing and I hate it, and I'm really sorry for what it's worth, but I didn't make the rules. I'm just the messenger. You want the most positive E cell for an oxidation. Aluminum going to aluminum 3 plus would be the one you'd want to choose in this list. These kind of questions pop up once in a while. Will tin reduce silver plus to silver? And there are some E cell values. And the answers are yes, no, which are more likely, or only if it feels like it, probably not answer C, but you never can tell. Anyway, pause the video, think about it. When you're ready to talk about the answer, unpause it, pause the video now. Okay, I'm assuming you've had a chance to work on it. You're ready to talk about the answer, so let's do it. Remember that if you're going to have a reaction, you have to have something oxidized and you have to have something reduced. And in the two half reactions that are given, they're both reductions. And to make any kind of chemical reaction occur, you have to have something being oxidized and something being reduced. Now, the question is, will tin reduce silver? Okay, it's not about silver metal, it's silver plus. So what that means then is that the tin and the silver plus are going to be our reactants. The tin and the silver plus are going to give you the yes, no, or only if it feels like, I suppose, answer. Okay, why that's important is that in the half reactions we have silver plus as a reactant, so we're going to use that one as is. Okay, but the second one, we don't want tin 2 plus as a reactant, we want tin as a reactant. So in the second equation, to make it look like the question, we need to flip it. We need to have silver plus plus tin making other stuff. All right, we don't care about what that is. We need tin as a reactant. So we're going to flip the second equation, and when we flip it, that's going to make positive 0.14 volts be the voltage. Okay, so if you take the 0.80 volts, which is good to go as is, and add positive 0.14 volts to it, that gives you an overall positive 0.94 volts. And all you really need to know is that it's a positive number. Positive numbers mean spontaneous, and that means that is going to happen. Tin will reduce silver plus to silver. All right, here's the overall balanced reaction. One of them has 2 electrons. You need to multiply the silvers by 2. But the important part here is that the positive E cell means this reaction is going to occur. That is going to happen. All right. So we use the E cells. If you flip a half reaction, you change the sign of the E. That's the only thing you do. And you just literally add them up together to see if you get a positive E or not. If that E cell would have been a negative 0.94, then it would have been non-spontaneous, and that would not happen, all right, by itself anyway. Here's a question. We have an E cell value and we want to determine the equilibrium constant for the same reaction. And there are a whole bunch of different possibilities there. See if you can remember what we did in this chapter to calculate the equilibrium constant. I encourage you to pause the video, work on it. When you're ready to talk about the answer, you can unpause the video, pause the video now. Okay, I'm assuming you've had a chance to work on this problem. You want to talk about the answer, so let's do it. The easiest way to do this problem is to remember that delta G equals minus RT natural log of K, but delta G also equals minus NFE. And really what we're doing in this problem is we're going to compare minus RT natural log of K to minus NFE. We're given the E value. We can find the Faraday. It's the Faraday constant, 96,485. N will be the moles of electrons transferred. And you can see that to go from chlorine to 2 chlorides, you need 2 electrons. So N will be 2. The temperature, 298 Kelvin. R is 8.3145. And you can find the equilibrium constant from there. Remember, to get rid of the natural log, you use the anti-natural log, the little e to the x button. E's that are positive correspond to delta G's which are negative, and negative delta G's correspond to K's which are greater than 1. So I would not expect answer A to be correct because that is a reactant favored K. You want to have a product favored K. So here's all the math, all right? And again, this is kind of the big part right here. Delta G equals minus RT natural log of K, which equals minus NFE. You can cancel out the negative signs. Natural log of K equals 2, which is the moles. I use 96,045. There's the voltage, 8.825. R and T. Natural log of K equals 64.2527. And to get rid of the natural log, you take the anti-natural log, e to the x button to both sides. 8.03 times 10 to the 27th is the answer I got out. So this is a cool way to go between an E cell value and an equilibrium constant. You could also get delta G along the way. Pretty cool. We have a voltaic cell created using the information below, and it's in Alaska where the average temperature is 5 degrees Celsius. Calculate the expected cell potential under these conditions. Now, there's a lot of information here. This one right here, this line, this is the shorthand notation for electrochemical cells, and this is something we talked about, but in a nutshell, electrons are going left to right. So aluminum is going to aluminum plus 3, and on the other side of the salt bridge, the double lines, nickel 2 plus is going to nickel. So that's kind of the overall process. So for the half cells, we do want nickel 2 plus going to nickel, but we want to flip this reaction around because aluminum's going to aluminum plus 3, not the other way. When you combine the E cell values, you should end up with a positive value. That's what voltaic means. However, these conditions are anything but standard. The temperature is only 5 degrees instead of the normal 25, and the concentrations of the ions are certainly less than 1.0 moles per liter. So we're going to need the Nernst equation on this particular problem. So I encourage you to work on this problem, pause the video, work on it. When you're ready to talk about the answer, you can unpause it, pause the video now. I'm assuming you've had a chance to work on it and you want to talk about the answer, so let's do it. When you're using the Nernst equation, all right, the Nernst equation is E equals the non-standard conditions. The Nernst equation, E equals E naught minus RT over NF natural log of Q. It should read E equals E naught minus RT NF natural log of Q. You do need E naught. And like I said, flip the aluminum reaction around, positive 1.66 minus 0.25, whatever that is, that's E naught. That's the standard conditions for this reaction. Then RT NF, R is 8.3145. The temperature would be 5 degrees in Kelvin, so 278 Kelvin in this case. N is the moles of electrons transferred. Now remember that the moles have to cancel out, and we have a 2 mole process and a 3 mole process. Common denominator of those two here would be 6. So N is going to be 6 moles for this reaction. When you make the things balance out, you're going to have 6 moles total. The F in that equation is the Faraday, 96,485. And the natural log of Q, that's where you want products over reactants. And on this reaction, aluminum 3 plus is going to be the product and nickel 2 plus is going to be the reactant. But aluminum 3 plus, you'll square it, and nickel plus 2, you're going to take it to the third power. And you've got the different values in there. So there's a little bit of math on this, but it's all stuff you can do if you break it down to these smaller steps. So let's see what's all happening here. First of all, the answer, 1.46. The balanced reaction here, 2 aluminums plus 3 nickel 2 pluses makes 2 aluminum 3 pluses plus 3 nickels. And we multiply those by 2 and 3 to make the electrons cancel. You don't want to show electrons, so N here is 6 electrons. 1.41 is the standard cell potential, E naught, and that's what number goes in right there. But because we're at non-standard, we have to do all this other stuff, minus RT over NF, natural log of Q. R, 8.3145, temperature at 5 degrees Celsius, 278. Here's the moles of electron 6, the Faraday constant, and then Q, natural log products over reactants. So for this reaction right here, we ignore the solids. It would be aluminum plus 3 to the second power divided by nickel plus 2 to the third power. And here's the aluminum, and there's the nickel concentrations. So at this point, it just becomes a lot of math, all right? The final value here for E, 1.46 volts. So if you got that number, you are good to go. So under these non-standard conditions, the reaction actually became more spontaneous, more product favored. And that's kind of a cool thing to think about. This question has to do with quantitative electrochemistry, and these questions usually are about length of time, which is what we're dealing with here, and you start with quantity and work to time, or they're going to be about quantity. How much can you make using so much time? And that's something we talked about in lecture. But in this problem, we have a current 2.00 amps, and it's flowing through gold, and we're trying to convert 0.0100 moles of gold 3 plus into gold. So notice it's going to take 3 moles of electrons to turn gold plus 3 into gold. Another thing I'll help you out with here, remember that amps means coulombs per second. So 2.00 coulombs are being delivered per second that this current is going through. See if you can use all this information to figure out how long it's going to take. I would try and find your answer in seconds, since they're all answers in seconds. Pause the video and you can work on it, and when you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem. You want to deal with the answer, so let's get into it. Like I said, these problems are usually either about quantity going to time, which is what we have here, or it'll say we're doing this for 15 hours. How much can we get out? So time to quantity, all right? That's kind of how these things all roll, and the process is pretty similar. So in this problem, you want to start with this many moles of gold plus 3, and you want to turn moles of gold plus 3 into moles of electrons needed, and that's where the 3 comes from. You need 3 electrons to make 1 gold plus 3 equal to neutral gold, so 3 moles of electrons are needed per mole of gold 3. Then the Faraday constant says that you have 96,485 coulombs per mole of electrons, so it allows you to go from moles of electrons to coulombs. And then finally that amp up there, the amps stand for coulombs per second, so if you divide by 2.00 coulombs per 1 second, you're going to get an answer out in seconds. So let's look at the math. 0.0100 moles is the amount you're starting with. 3 moles of electrons needed per gold 3 plus to make them neutral. Faraday is 96,485 coulombs per mole of electrons. And then the last thing, 2.00 amps means 2.00 coulombs per second. So you can see you need to divide by the amps. You'll have seconds in the numerator, the only unit left standing. 1,450 seconds are required to make this gold transfer using a 2.00 amp current. Oh joy. Okay, that's the end of the review. I really appreciate you spending your time with me. I hope this was helpful getting you ready for the second midterm. If you need more assistance getting ready for the midterm, I do encourage you to check out the practice problem sets, which are online and in the companion. They'll help you get ready for the material, and the answers are found in the back, so you can make sure you're doing good. Concept guides are worked problems. I do encourage you to check them out. There's chapter guides online that have a lot of video and digital kind of things to help you with this material. And also the textbook itself has a lot of end of chapter problems. And at the end of the textbook, basically every other question has the answer at the end. So you can try the question, check yourself in the back of the book, make sure you're doing great. It's pretty cool. You totally have the skills to do this stuff. All right. I know there's a lot of material, but man, you can totally do this. You've made it this far. We're almost to the end of the term. So you just hang in there a little bit longer. I can't help you with the midterm itself, but I can help you prepare for the midterm. So if you have questions on these things that to prepare for the midterm, please let me know. You can also ask the Learning Success Center / Avid Center for help preparing for the exam. Don't ask them for help on the exam, obviously, but you can have them help you prepare for the exam. That's totally cool. All right. I wish you the best with your studying. Have a great day, and thanks again for spending your time with me.